Here we have a horizontal spring that has a block attached, and that block has been pulled back a distance a away from the equilibrium position, compressing that spring. And let's say that the spring has a spring constant of k. When I release this block, as long as the spring obeys Hooke's law, then this block will oscillate back and forth in simple harmonic motion. And I'd like to think about the energy of this oscillator as a function of time. How does the energy get exchanged from one form to another as the block oscillates back and forth? For starters, I know that in the instant drawn there in the picture, there is some potential energy in that spring. Due to the fact that the block has compressed the spring a certain amount, it has some potential energy stored in that spring. And we know that that's true because if we let go of the block, then all that compressed energy in the spring there is going to shoot the block out and make it move to the right. And I know that the equation for the elastic potential energy that's stored in that spring is in general equal to 1/2 k x squared, where x squared represents how far the spring has been stretched or compressed. At the equilibrium position, the spring is at what we will call its rest length. So the rest length occurs at the equilibrium position. It's important that you know I'm defining the equilibrium position as the place where the center of mass of this block would be at when the system is at rest. So say I let go and the system oscillates back and forth and eventually it stops. The center of mass of that block would stop at the equilibrium position, and when that happens, the spring would be at its rest length. It's not compressed or stretched at all. And in that case, the x value in my elastic potential energy equation would be 0. There would be no elastic potential energy in the system because the spring's not stretched or compressed. But at the position as I've drawn it there in the picture, it is a distance a away from the equilibrium position. So if I wanted to, I could express the elastic potential energy as 1/2 k times a squared, where a is the amplitude that I've given it when I've pulled it back. I also know that the block is not moving, and if I define the place where the block is right now to be the place where the gravitational potential energy would be 0, then there's no other energy associated with the initial position of the system as it's drawn there. And so not only is the elastic potential energy equal to 1/2 k a squared, but that's the only type of energy present in the system. And so for that reason, I'm going to say that the total energy of the system, E, is equal to 1/2 k a squared. So in general, for an oscillating system like this, we'll define the total energy of the system, E, to be related to the initial amplitude that the system has. And so the expression of that equation is 1/2 k a squared. Had I given it an amplitude of 2a, twice as much amplitude, then the expression would be 1/2 k 2a squared, and there would be 4 times as much energy in the system. So I now know that at the negative amplitude, the energy is all elastic potential energy. Now let's look at the equilibrium position. At the equilibrium position, the spring would be at its rest length, which means it's not stretched or compressed. That means that the elastic potential energy would be equal to 0. So where did all the energy go? All of that energy now has been converted into kinetic energy. The kinetic energy of the system at the equilibrium position would be equal to 1/2 mv squared, but not just v squared. I'm going to write v max squared. Because at the equilibrium position, the velocity of this block is its maximum value. And so the total energy of the system could also be written as 1/2 mv max squared. Because I know that at the equilibrium position, the only type of energy present is kinetic energy. And as you might imagine, when we move over to the positive amplitude, the same thing is going to be true at the positive amplitude as was true at the negative amplitude. And notice that the distance from equilibrium, A here, is squared in the equation for elastic potential energy, and so it doesn't matter if we're talking about the negative amplitude or the positive amplitude, the energy associated with that position will be positive. And so at the positive amplitude, I could say that the elastic potential energy is given by 1/2 Ka squared, but I could also say that the total energy is given by 1/2 Ka squared. So that's what happens at the negative amplitude, the positive amplitude, and the equilibrium position. But what is true of the energy at a location that is, let's say, 1/2 A? So minus 1/2 A, or plus 1/2 A. You might be tempted to think, well, if it's all kinetic energy at the equilibrium position and all elastic potential energy at the maximum amplitude, then halfway in between, we should have half of each type of energy. And while that's an incredibly reasonable thing to think, that's completely wrong. And so how can I figure out how much of the energy is kinetic energy and how much of the energy is elastic potential energy at any particular position, like 1/2 the amplitude? The way that I would show that is the following. I would say that at 1/2 the amplitude, the elastic potential energy would have in a form of an equation that looks like this: 1/2 K, but instead of A, the amplitude at this location is just 1/2 A. So the elastic potential energy term is equal to, I'm going to write this in kind of a strange way, 1/2 Ka squared, and then the 1/2 inside the parentheses would be 1/4. Okay? I'm writing it in this way because everything inside the parentheses here, the 1/2 Ka squared, is exactly what I wrote for the total energy at the maximum amplitude. And so if 1/2 Ka squared represents the total energy of the system, then the way I can express the elastic potential energy is the elastic potential energy at 1/2 A is equal to 1/4 of the total energy. So the elastic potential energy at 1/2 the amplitude is equal to 1/4 of the energy. If that's true, then how much of the energy is kinetic energy? If 1/4 of the total energy is elastic potential energy, then that means that the other 3/4 of the energy must be kinetic energy. And so at either one of those positions, at half the amplitude, 75% of the energy is kinetic energy and 25% of the energy is potential energy. And one reason why I know that to be true is because at any moment in time, so long as no energy is being removed from the system, the total energy needs to remain constant. And so I see here that the two terms that I just wrote, the elastic potential energy is 1/4 the total energy, and the kinetic energy is 3/4 the total energy. Those two terms would add up to the total energy E. 1/4 E plus 3/4 E is just E, which is equal to the total initial energy that the system had when I pulled it back to its negative amplitude. So now I'd like to go ahead and look at a graph of the energy as a function of position for this system. So what would that look like? And so we're going to make a little graph with just one axis that has at each point the energy that's associated with that position. So I know, for example, that at the negative amplitude, all of the energy is elastic potential energy. At the positive amplitude, all of the energy is elastic potential energy. And at equilibrium, the energy in the spring is 0. And so this red line I'm going to draw is associated with the elastic potential energy. And I know because the elastic potential energy is proportional to x squared, the position or that stretch distance squared, then the relationship between these two things will be parabolic. And so my graph looks something like this, where on either side of the equilibrium, the elastic potential energy increases in that parabolic kind of fashion. Now for the kinetic energy at either amplitude will be 0, because as it approaches either amplitude, it slows down before stopping and then turning around and going in the other direction. But then at equilibrium, the kinetic energy will be a maximum, but not just some arbitrary maximum value. It will be an amount of kinetic energy that is equal to the amount of elastic potential energy that the system had when it was at its maximum amplitude. And so this graph is also parabolic as it increases as it gets toward equilibrium and then decreases as it moves away from equilibrium. And so what we find is that if we choose, for example, that position of 1/2 A, then although my graph is poorly shown, if we were more careful about this, we would get closer to the relationship that I've shown on the left there. But the potential energy is quite low, and the kinetic energy is much higher than that. Now, perhaps this graph isn't the best evidence of proving that 25% of the energy is elastic potential energy and 75% of it is kinetic energy, but that's something you could measure for yourself. But given the relationships that I have here, at least you can see, even with my poorly drawn graph, that substantially more of the energy is associated with the kinetic energy at half the amplitude. If I wanted to draw a line that represented the total energy as a function of time, then it would probably look something like this, right? It would start here, and it would just be a horizontal line that continues on. And so perhaps that line represents the total energy, which would stay constant. And so how could I summarize all of what we're learning here in a useful kind of way? The energy at any particular moment in time, so not particularly the points that I've addressed here, but just any arbitrary point, would be equal to 1/2 kx squared, the potential energy at that location, plus 1/2 mv squared, whatever the kinetic energy is at that location. And in terms of problem solving, if I look back to the initial equation that would describe the total energy of the system, notice how, so long as that block is on a frictionless surface, none of that energy is being removed. So at all moments in time, if I just know that initial amplitude and the spring constant, then I could very quickly calculate a number using that equation 1/2 Ka squared. And that number would represent, in joules, the amount of total energy present in the system. And so if I knew that number, you could imagine using the equation that I've written here and setting that number, which represents the total energy, equal to 1/2 kx squared plus 1/2 mv squared. And for example, in a problem being given some arbitrary position, right? So when the system is 1 centimeter away from equilibrium, or when the system is 1/7 of its amplitude away from the equilibrium. And using that number, and using the number for the total energy to solve for example, the velocity. And so I could determine how fast this system would be moving at a particular location, knowing things like the mass of the block, the spring constant, and using the initial amplitude to determine the initial total energy. I would also like to reiterate the idea that this calculation that I've shown on the left in blue is an extremely important kind of calculation. I can always express either type of energy as a fraction of the total energy, which can be expressed as 1/2 Ka squared. It's crucial that we understand that. Lastly, I'd like for you to go to O-Physics, spelled as it is at the top of the website title there, and go to Waves at the top and go to the second simulation that's listed, where you can find a system like the one that I talked about in this video, and you can see graphs of energy as a function of position, several other graphs like position, velocity, acceleration, and types of energy. It's a tremendously helpful simulation for trying to understand the things that we're learning right now.